Hello and welcome to video lecture number 12, which covers section 1.8, day 1, combinations of functions, composite functions. By the end of this lesson, you will be able to calculate various operations on two functions, and you will also be able to compose two functions together. A summary of the four main function operations is given to you inside the box. I encourage you to take a moment to read through it to help you better understand what will come to follow. In example 1, we are given two functions. The first function, c of x, represents the cost to a certain company based on every unit they sell of a particular product, x. The second function is a revenue function that tells us for every product they sell, they earn $17.98. In part A, we're asked to find the domain of the first function c. Using interval notation, we will do that. Now, this is a linear function, and typically the domain would be negative infinity to infinity. However, this is a real-life situation. So you have to consider x, and x is how many or the number of products that they sell. Well, you can't sell a negative number of product, therefore the domain begins and includes 0 and does go to infinity. Now, it's probably not realistic that they could sell an infinite number of this product, but we will use that to save us a little bit of time. Looking at the revenue function also has the same variable x. How many of this product did they sell? Well, at the same time, they can't sell a negative number of product, so our domain will also be 0 to infinity, including 0. Now, the intersection of these sets is what are the x values that belong to both of these? Well, since these are the exact same domains, the intersection of the two domains would still be 0 to infinity. This is where the domains overlap, so to speak. Part B asks us to find the difference of the two functions r and c. So using the definitions above, the difference of the two functions simply means let's subtract them. Well, I'll start with the function r of x, which is 17.98x, and we will subtract from it the cost function, 12.30x plus 98,000. Next, we will simplify anything that we can. The first thing that I've done is distribute the negative to both the 12.30x and the positive 98,000. Finally, I combine the like terms, 17.98x and 12.30x, to get 5.68x minus 98,000. Our domain is the intersection of these two sets, which we found earlier. Since x is still the number of products sold, you cannot have a negative number, and the domain will remain from 0 to infinity. Part C asks you to interpret your answer from Part B, and that function, revenue minus cost, will give you what is known as profit. After we take away what we paid for something from how much we made from it, hopefully we're left with a positive value, and that positive value is known as profit. Example 2 gives you three functions and asks you to perform various operations with each of them. In example 2a, you're asked to find the domains of each individual function, and I've written them for you below. Now recall that all of these functions are either quadratic or linear, and all quadratic and linear functions will always have a domain of negative infinity to positive infinity. I'll begin by trying example 2d with you. 2d asks us to find the product of the functions g of x and h of x. So I start by replacing each symbol with its function listed above. Now, since you have two terms in each set of parentheses, what you need to do to multiply them is use the FOIL method or double distributive property. So using the FOIL acronym for distribution, I will distribute the 2x to both terms in the set of black parentheses. 2x times x squared is 2x cubed, and 2x multiplied by negative x is negative 2x squared. We now must take the negative 2 and distribute it to both terms inside the black set of parentheses as well. You see the result of distributing the negative 2 to both terms in green. Now we will combine any like terms that we can, and both negative 2x squared and negative 2x squared are like terms. When you combine them, you get negative 4x squared. We then will carry down the terms we did not combine, and we are left with our final simplified product function. Now it also asks you to write the domain, and the domain of this function is that same domain that we found at the very beginning. Those two original functions both had a domain of negative infinity to infinity, so this new function will also take on that same domain. Example 2e asks us to find the quotient of f and g, and we will first start by considering the domain. Remember that you cannot have 0 on the bottom of a fraction, and the value of x that would create a 0 would be 1. So we cannot have 1 in the domain of this function. Now we will attempt to simplify it. What may appear as a dead end is really not if you use the concept of factoring. I've factored both the numerator and denominator using two different methods. The numerator is a quadratic trinomial, so we can ask ourselves what two numbers multiply to 4 and add to negative 5, and the result is what you see in the parentheses. The bottom, both terms have a 2, so I will factor that 2 out. When I do that, I now see a common factor in the numerator and denominator that we can then cancel out. So the simplified quotient would be x minus 4 over 2, and if we divide both of those values by 2, we will get something that looks more familiar, 1/2 x minus 2. Now, this is a linear function, but remember where it came from. It came from this original quotient, and remember the domain of that, x could not be 1. So since our new simplified function came from that restriction, we must also include that restriction in our domain. So negative infinity comma 1 union with 1 to infinity, which is another way of saying x cannot be 1. So please try the remaining parts of this example that I have not shown you on the video and have them ready to check for tomorrow. Part 2 of this lesson describes composition of functions. The definition of a composite function is a function formed by using one function as the input for another function. Typically, you plug in single values into functions, while composites are when you take an entire function and plug it in to another one. There are two ways to symbolize this, and the first one you see on the left, and the second one you see on the right. Notice the g of x is the input function, and that would be in both cases. So typically the one on the right is a little easier for students to understand this input idea. You pronounce each of these symbols accordingly. The one on the left we would say f of g of x, and the one on the right we could say the composite of f and g. And you can use these interchangeably depending on the symbols, but notice that the symbol f of g of x on the left here, that open circle, does not mean multiplication. That means composite functions. So be very careful about when it's asking you to compose versus multiply two functions together. So I would like to show you a diagram that helps better explain what composite functions do. So on the left, I filled in some random x values. Those x values are 1, 2, and 3. Now suppose you have the function g of x, which doubles all of those x values. So that would mean 1 would become 2, 2 would become 4, and 3 would become 6. The function g of x would be 2x. Now, if you take those values 2, 4, and 6 and perform another operation on them, let's call this the function f of x, which will be 3x minus 1, we will get the values 5, 11, and 17. Notice we started with a certain set of x values, 1, 2, and 3. They became 2, 4, and 6 as the result of one function, and those values became 5, 11, and 17 as the result of another function. Well, what does the composite function do? The composite function would be the function that would take the values of 1, 2, and 3 on the far left and map them directly to 5, 11, and 17 by essentially cutting out what you see in the middle. When you are dealing with domains of composite function, it is very, very important to understand that the domain of the composite function will take on the domain of the input function. So if you have f of g of x, then the domain of g of x is the domain of the overall composite function. Example 3 asks you to perform various function composition with 2 of the 3 given functions. So I will try example 3a with you. I start by writing it in the alternative notation f of g of x so that you can better see that g of x is the input function. This is what we will substitute into the function f. So I've replaced g of x with x squared plus 4, and I must plug that in for the function f wherever I see the variable x. So you are not plugging in just a single number. Now you're plugging in an entire expression, x squared plus 4. So the function f acts as our outline or base function, and the function g acts as our input function. Now we will simplify. I will then take the 3 and simply distribute it to both terms in the parentheses, and I result with 3x squared plus 12 and minus 1. Well, that leaves me with 3x squared plus 11. Lastly, we will find the domain of our composite function, and recall that with composites, the domain will always be the domain of the input function. Since the domain of the input function is negative infinity to infinity, that will also serve as our domain for our composite. Please try example 3b on your own, and now I will show you 3c. Once again, I begin by rewriting it in a function form that is probably a little more user-friendly. Now, notice that g of x, once again, is our input function. Next, I will replace g of x with x squared plus 4, and this hopefully makes sense that you will plug x squared plus 4 into the function h. Substituting x squared plus 4 in for x into the function h of x results square root of x squared plus 4 plus 3. By combining the 4 and the 3, I am left with x squared plus 7 underneath the square root. At this point, we cannot simplify it any further. The last thing we'll do is write the domain of our new composite function, and remember, the domain of our composite takes on the domain of the input function. G of x was once again our input function, so the domain of our new composite function is negative infinity to infinity as well. So together, this would be our answer. The last example I will try with you is example 3D. Now notice this does look a little different than the ones previous because there is a value next to the composite. So rewriting this, I have f of g of 8. There are a few ways to approach this, but I've decided to take the value of 8 and plug it into the function g first. Recall that the function g is x squared plus 4. By plugging in 8, I can then calculate and get a single value. So by calculating 8 squared plus 4, I am left with the value of 68. At this point, we are being asked to plug in 68 into the function f. Now using the function f and inputting 68 in for x, we are left with 3 times 68 minus 1. After using multiplication and subtraction, we see that the value is 203. And this then is the equivalent of f of g of 8. This is our final answer, and we cannot find the domain because we have found a function value, not a new function altogether. So please try the remaining parts of example 3 on your own and have them ready to check for tomorrow. So this concludes video lecture number 12. If you haven't already been coming up with a list of questions throughout watching the video, please take the time to go back and reflect and come up with at least one question you still have after watching. Thanks for viewing, and good luck.